c'est...
Ça marche?
Je sais pas. Bonjour. Bonjour à tous. Nous avons le plaisir de recevoir Valentina Balbi. Sébastien Nurkic m'avait donné un papier avec la bio de Valentina. Je l'ai perdu. Donc du coup, on va le faire ensemble.
Oui.
Donc Valentina, elle est actuellement avec Michel Lestrade en Irlande avec une bourse Marie Curie où il va nous présenter ses travaux. Avant, elle était postdoc à Manchester où elle a travaillé sur des matériaux viscoélastiques. Et avant ça, il a fait la thèse ici, dans notre laboratoire, avec Pasquale et Charletta, actuellement en délégation infinie à Rome, à Milan.
Milan, oui.
Oui, c'est pas ça, non? J'ai filmé, merde. J'ai fait ça. Où il a travaillé sur des croissances des milieux biologiques. Et avant cela, comme son nom ne dit pas, il vient d'Italie. Il a fait une ingénierie mécanique, ingénierie mathématique
oui.
au Polytechnique de Turin.
Oui.
Et donc, ce qu'on va voir aujourd'hui, c'est tout ça, ce qu'il a fait pendant sa trajectoire scientifique, c'est-à-dire de la géométrie, des maths et de la biologie.
Et de la mécanique.
Et de la mécanique.
Ok, merci. Merci aussi pour l'invitation ici. Je suis très contente d'être revenue dans le labo et de voir des gens qui je connais et des gens nouveaux aussi. Je suis désolée, mais je pense que je vais faire le talk en anglais parce que mon français il s'est un peu perdu, au moins le français technique plus spécifiquement. Donc je suis désolée, mais je vais parler en anglais. J'espère que ça va aller quand même. Okay, so my talk today is going to be about the mechanics of a twisted brain. So, I don't know what you think the topic is, so if you can give me some thoughts about what twisted means for you, and what do you expect from it, from this word. Don't be shy. Crazy. Yes. No, I'm not going to talk about psychology or crazy people. I'm going to talk about the twist of a brain, so the mechanical twist of a brain. So what happens when the brain undergoes a torsion? That can happen, like in this situation, or during a car accident, or again during very aggressive sports like rugby or football. Here, for example, we see the boxer and the football player and the rugby players are going through rotation of the head in the what is called the horizontal plane of the brain, like this. The same for the girls and for the rugby players. And here, what is happening is a rotation in the corner, in the sagittal plane, which is this one. Okay, so all these scenarios involve rotation of the head and thus a rotation of the brain. So we were interested in understanding what's the damage caused by a rotation of the brain during a traumatic experience. And so all these examples I gave you here are induce what is called traumatic brain injury. So it's a damage of the brain caused by an external force. But it can also happen, for example, for if you are stabbed in the brain, like a blade penetrates your skull and goes through the brain. That's also causes traumatic brain injury. And here I just give you some statistics from Bionic collected in 2010-2011, showing what are the main causes of traumatic brain injuries in children in between 0 and 15 and 19 years old. For example, you can see that motor vehicle accidents are not very significant, but for example, falls are a major cause for very young children, and recreational causes like sports It's very high in, it's a major cause in children aged in between 10 and 14 years old, and assault for older children. Okay, and so TBI, it's not so easy to detect, because maybe people have symptoms that arise later after the impact. So people, maybe they don't notice they had a brain injury, and then if they're not treated in time, they die. Okay, so a particular type of traumatic brain injury is diffuse axonal injury. And this happens when acceleration and deceleration are involved in the impact. For example, if you are stabbed, that's not going to cause diffuse axonal injury, because, well, you need acceleration and deceleration. Like a car accident or an accident during sport, these can cause axonal injury. And what it is a damage at the level of the cells. So neurons get damage, and it's a permanent damage. So it's not, you're not going to recover from it, and that's very, very, very dangerous. Okay, and there are two types of impacts and deformations that can lead to diffuse and axonal injury. One is the linear acceleration, so maybe translational movements that can cause compression, tension, and shear of the brain. Like if you go against the wall like this, your brain is going to do like this, right? So it's going to be compressed, stretched, and it's going to shear against the skull. And there's a lot of literature about it, so people can predict what happens in the brain after these kind of impacts. And they found out that basically what's important is how much strain is gonna suffer the brain. So how much is gonna be stretched or compressed at, in terms of strain, so of like deformation, if you want. But it's also a combination of the speed, so of the strain rate at which the strain is applied. So, and so in this paper by Morrison's and colleagues in 2006, they gave a threshold for strain and strain rates that can lead to diffuse axonal injury. And they say this, if your brain experiences a strain bigger than 0.1 and at a strain rate bigger than 10 per second, then your axons will suffer, will be damaged. But what happens when a rotation, so a rotation is applied to the brain? We don't have any thresholds, and that's what we are aiming to do with Michelle in Galway. And that's important because, for example, for helmets used in rugby or football, you want to build the helmet in a way that is able to absorb not only forces caused by linear accelerations, but also by rotational accelerations. So yeah, okay, so I said that the axons, so the neurons that are the cells at the base of the brain are damaged. But how this happens is that, so these are the cells in the brain, neurons. These are nuclei. These are the axons that link the nucleus to the synapses, and then they are all connected together through these synapses. So you can imagine, so the electrical signal passes through the axons and is transmitted, and also so do some like nutrients and other molecules. So you can imagine if you stop the connection through the axons, no electrical signal will go through, and no molecules. So the part of the brain that is beyond the point of breaking is gonna die. And how do we see this from an MRI scan? We see black dots, because at these points stuff accumulates, like nutrients or whatever, fluids, and so the axon is gonna swell, and that's how we see black dots from an MRI scan, and it's gonna be diffuse in a that's why it's called diffuse axonal injury on a big area of the brain. And you can also spot dots in different locations. So it's important to be able to predict where this breaking is going to happen. And the breaking happens because of a stretch and twist of the axons generated by the impact and by rotation and by different types of deformations. Okay, so what can we do as mathematicians to help in this big mess? So if we know, so the best we can do is to be able to reconstruct the impact of the accident and tell the doctors where we think that the brain is going to be damaged, right? And where the axon is gonna break. But to do that, we need to know the dynamics of the accident, so know the force involved, the speeds, the accelerations, the type of impact, if it's a rotation or a translational impact. Then we can build up a model of the head, but we also need to know to build up a good model of the brain. So not only the head with the skull, the scalp, but also the brains with all the components that of course will behave maybe differently, mechanically differently. And once we know all these details, we can build up a finite element model and do the simulations to simulate the impact and predict where the region of highest strain are going to be. Okay, so with Michel we are working, so with finite elements, it's important to know and to use the right mechanical properties for the components of the model, right? So if you don't use the right numbers for the shear modulus of the brain or of its components or of the skull and of all the other components, we will get wrong results, right? So with Michel we are working on determining the mechanical properties of the brain itself. And there are nowadays two main currents of thoughts about how getting these numbers, so elastic and viscoelastic properties of a tissue. One is non-destructive, so you don't need to take a brain and do experiments with it. You don't need to kill somebody and take his brain out with acoustic waves. You can just open his skull, which is halfway invasive, and then you send a wave through the brain. You wait that it comes back, and you can see, depending on how the speed changes, if there are changes in stiffness, for example. That's very useful for detecting brain tumors, for example, because they are much stiffer than the healthy tissue. All right, so the wave is going to change speed when it passes through healthy tissue and then tumor. And then, of course, there are destructive mechanical tests, which involve having a brain and testing it with mechanical devices, right? And at the moment, there's a group in Dublin that is doing that. So Michel worked with his PhD student Badar and Michael Gilchrist in UCD, University College Dublin, and they conducted tests on fresh pigs' brains in tension, compression, and shear. And then there's Ellen Kuhl's and Gerard Holzapfel's groups in Graz and Stanford University. They are doing multi-axial deformations, so they're combined. They have tension, compression, a machine that can do everything basically. So all these deformations are superposed. So you have basically more information from coupled mechanical tests. But they used frozen human brains. And then there are indentation tests. Ellen is also doing indentation, but also in UCD they did it on mouse brains. So the thing is that there's a lot of variability in the data, because using a frozen brain is not the same as using a freshly extracted brain. So, well, with Michelle we tried to, well, we did we went through the second way. So we did destructive mechanical tests on pigs, fresh pigs' brains, and I'm gonna tell you how. So as I said, we work on brains, fresh brains. So I'm gonna show you some pictures of brains. I hope. Well, I find them nice now, but maybe I can understand that it's not that nice for somebody that does not work with brains every day. Okay, but it's not coming yet. So it's the first time I do this talk, so I still don't have. I don't remember what I put first. Anyway, okay. So the first problem we encountered was to find a machine that was able to do torsion tests on biological tissues, especially brain, because the ranges of forces we are talking about is very, very low. So classical mechanical devices used on metals or hard composites, they don't have enough sensibility and sensitivity and accuracy to do those tests. So we found this machine called a Rheometer that is usually used to characterize fluids and viscosity of fluids, but it has a very useful function. Well, what it does is basically rotates a plate, but it measures both torque and normal force required to rotate something. So rotate the sample that is in between the plates. And so information on the torque is pretty common to get, but the normal force, that's very unique, because the normal force gives useful information on what is called the pointing effect. So the ability of a nonlinear material to extend or contract in the direction perpendicular to the torsion or to the shear. It works the same for the shear. Okay, and so up to now, nobody has quantified the pointing effect for brain tissues. Okay. Okay, so here we go. First step was extracting the brain from the pig's heads. I know, sorry. That's a pig's head. It's very different from human's head because they have a very, very thick skull on the frontal part. So here the cut is going to be down to 4 centimeters, like this. So it's very, very thin, and it's very thin on the bottom part. So we use a saw, an electrical saw, to take out the skull, and then that's the brain inside. Is still covered with the dura mater, and that's the brain after extraction. So after 2 hours of hard work, I put muscles on after these months, and to get a very, very small amount of tissue, because the brain here is, I don't know if you can see it, but it's only 6 centimeters per 8 to 9 centimeters. So from a brain, we can get maybe 10 to 15 samples, and we needed a lot, like 150 samples in total. Okay, so once we got the brain, we had to cut it in. So I didn't say it, but the Rheometers works with cylindrical samples. So we had to get cylindrical samples from brain, and we did it with a cylindrical punch. of diameter, yeah, the diameter was the same as the plates of the rheometer, and if I remember correctly, were 2 centimeters. Was 2 centimeters. And then the height was much more complicated to get because we had to use a scalpel to cut from a longer cylinder, smaller cylinders. Anyway, we extract the samples from 2 different planes. So on the left, samples are taken from the horizontal plane, so like this, so that this is the brain, and we punch it like this. Okay, and then on the right, we first slice it, and then turn the slice on and punch it. So the samples on the right are taken from the coronal plane, and we did that because we thought that there was a difference between, like a mechanical difference from the 2 planes. Okay, and then we started with the tests. So okay, the machine was, well, we had to transport the samples, but anyways, we used PBS solution to store them, and all the experiments were done in between 2 hours after the extraction, so the brains were still in a good state. Okay, and we glued the samples in between the plates using surgical glue, which doesn't like damage the tissue. We set the normal force to 0, so we were sure that at that point the brain wasn't compressed or stretched. And then we set the speed at which we wanted the plate to rotate. We considered 4 different speeds, apparently very low, but you will see that they were high enough. And then we started the test for 10 seconds and repeated for 5 different samples. So for each strain rate, for each speed, we got at least 5 tests. Okay, and here I'm gonna show you how the tests look like. So that's the sample, and it rotates. Okay, I'll not show it again. So what happens, you saw it, it's that the brain at some point very early it breaks. So it's so brittle, so soft, that the test is very short. Okay, so the results. I told you before, the machine records the torque and the normal force required to apply a certain rotation to the sample. Okay, so here we are looking at 2 pictures, because one is from the test in the horizontal plane and the other is for the test in coronal plane. Okay, on the x-axis we have the twist. So the twist is the angle of rotation divided by the length, because the samples didn't have the same length, so we had to normalize in a sense. And then the colors refer to the different speeds, to the different strain rates. So yeah, so 0.5 is a very slow test, and 3% is a very fast test. Okay, so looking at the pictures, what do you get from them? What's the trend? It's like a linear, parabolic, quadratic, logarithmic, exponential. Huh? Sorry? So the slope of these lines will give us information on the shear modulus, basically. But the thing I wanted to point out is that they are lines, so the trend is linear. Okay. Can you see it? Oh, okay, good. Okay, and these are the results for the normal force. can you see it again that it's linear? Maybe a bit less linear, but I'm confident it's linear. Yes. Yeah, it's a bit up here.
So if the curves don't
Yeah.
zeros,
Yes.
they are not linear, they are affine.
No. Okay. No. Well, there's an explanation for this. It's because I'll talk about it in the next slide. No, but it can be that it's linear, but it doesn't start from 0. Okay. What?
Affine is a curve like AX plus B.
Yes, okay. Yeah, that was yes, that's the case in fact. Okay. Because it's linear in phi squared. But no, you have to remember this, that the torque is linear with respect to the twist, and is the normal force is linear with respect to the twist squared. That's very important because there's a very simple model in hyperelasticity that can reproduce this behavior. Do you know which one? No, it's like a generalization of the Neu-Hookean, is a Mooney-Rivlin material. Yes. Okay. Okay, so here we go. How can we model and how can we get the same, like reproduce the experiment, right? So we have information on the torque and on the normal force. So maybe so the deformation is a torsion, and we are happy with it, right? So we are twisting this cylinder like this, and we can write it like this. Yes? Where phi is the twist, so angle per unit length, and lambda is a stretch. And that this lambda, we had to introduce it because of this shift in the curves we saw before. And that's because, in fact, it's not the the results don't are not good, then we change them. It's not like that. So we have a reason to introduce the lambda, right? And that's because the plates that are acting on the sample, they induce a small compression of the sample. Okay, so even if after calibration the normal force is 0, the force that the effect of that force on the sample is still there, so the sample is gonna be a bit compressed. Does it make sense? So that's the reason why the lambda is there. It's not that we invented it, there's a physical reason. And in fact, upon introducing the lambda, the fit on the data is much more accurate. Anyway, okay, so to get the torque and the normal force, we know the deformation, we solve the equilibrium equations, where the boundary conditions are 0 stress on the outer radius, because the cylinder was not constrained, so it was free of stress on the outer surface. Okay, so what we need is a constitutive equation for sigma now. For sigma is the stress, Cauchy stress. Are you? Yeah, you are familiar with this, right? Okay. Okay, so we made few assumptions, which are idealistic, but it's the best we could do. So we assumed that the brain was isotropic, incompressible, and homogeneous. Okay. And then, yeah, I pointed out earlier that you remember the torque depends linearly on the twist, and the normal force depends linearly on the twist square. So the best model that can capture this, the easiest model that can capture this is the Mooney-Rivlin model. So now that we have Okay, the parameters in the Muni-Rivlin model are these C1 and C2. Maybe you're more familiar with the shear modulus, which is 2 times C1 plus C2. Okay, anyway, from these two parameters we can calculate the shear modulus of the brain, so how stiff is the brain under torsion, basically. And with C2 is gonna tell us about the pointing effect of the brain in torsion. And these two are the parameters we want to estimate from the data we got. Okay, and equation 4 is just a constitutive equation for a Muni-Rivlin material, where W1, W2 basically corresponds to C1 and C2. So wherever you see W1, W2, think about C1, C2. Or, yeah. Okay, and P here is just the Lagrange multiplier for the incompressibility. Yes? Okay, so once we solve the equilibrium equation, we have basically a relation between the measured torque and normal force, the twist and twist square, those are all things we know from the experiments, and we have these constants A, B, B, C to estimate, and A, B, C are related to the mechanical parameters that we really are interested in, that are W1, W2. Okay? Well, it's a bit of maths, but so once we do the fitting on the data, we basically get this number A, B, C. That doesn't mean anything to us, but we can convert them to W1, W2. Okay? And then R0 is the initial radius of the cylinder, and lambda is the stretch. We calculate also the stretch, but it's not very, it's not what we are interested in. Okay, this is just to show you how the fit works. So the dots are the data and the lines are the model. So yeah, so a good fit for us would be an R square bigger than 0.9. Usually don't accept anything that is below. And here you can see that with the Muni-Rivlin model is a really good model to fit this data. This is the torque, and that's the normal force. I think for a sample tested at 1 per second. Yes, 1 per second. Okay. Okay, so now what we have done so far are the experiments. We got the data, we fit the data, we found a good model that works, and we got the mechanical constants for the brain under torsion. And these constants are the shear modulus. So from W1, W2, I told you before, we can calculate the shear modulus, which I called mu here. And here is a plot of the estimated mu for the different speeds. So these are tests at 0.5 per second, 1, 2, and 3. And the box plot are the medium values with the first percentile. It's basically how the parameter mu, the ranges of the value estimated for the parameter mu, and the green boxes are for the tests in the horizontal plane, and the yellow one are the tests in the coronal plane. So basically what we see is, for example, that as for 0.5 and 3, so well, the trend is that mu increases with the speed. So the fastest we do the test, the higher the modulus is going to be. So the stiffer the brain behaves when it's twisted. And the same trend is, we can see it both for in the coronal and in the horizontal plane, okay? Because it's increasing, well, almost increasing, roughly increasing. Okay, the asterisk up there means that there's basically a statistical difference between the values got at 0.5 strain rate and 3 per second. So it means that if we do the experiment very slow or very fast, we are going to see a different behavior, basically, so that we cannot neglect. And the same is for tests at 1 per second or 3 per second. Like if we do a test at 2 per second or 3 per second, we would not see very much difference. But if we do it at 0.5 or at 3, then it would change. Like the modulus will change a lot. Okay, and these are the results for the other parameter, the W2, the one that indicates the pointing effect, basically. And here again we see that the trend is increasing for increasing speeds, and again that there's a statistical significance in between tests at 0.5 and 3 and 1 and 3. And okay, so to get these results, we did a post hoc Taki test. It's a statistical test, basically, to test the significance of the results and like the effect of the speed on the parameters. Okay, almost done. Okay, now I wanted to compare the results we got on the torsion with those on the shear, because we see that 0.5, 1, 2, 3 per second are not very high speeds, right? You can imagine it's a very and even the test, it looked very slow. So I thought, well, comparing to the experiments that Michel's PhD student Badar did in 2013 on shear, on brain in shear, he found this. So for 30, 60, 90 and 120 per second, he got these results on the right for the shear modulus. Okay, and our tests were at 0.5, 1, 2 and 3 per second, so very low speed. But nonetheless, we found that the shear modulus was in the same range as for the shear test. So it means, how did we compare this is using the strain gamma, that in shear is the, so the experiments in shear, the tests are done moving the upper plate horizontally. So the shear is going to be the extension, like the displacement of the horizontal plane divided by the height, and the height is constant, so it's basically x. And is also the tangent of the shear angle, basically. Whilst in torsion, the strain is given by the rotational angle multiplied by the radius and divided by the length of the cylinder. So that's, we use the strain, these measure of strain to compare the results. Yeah, and so what we found is that even for slow, for lower strain rates in torsion, we get very high, a very stiff behavior. The same range of stiffness as for very fast tests in shear. Okay, so what we have done so far is to perform the mechanical test on fresh brain in torsions. We estimated the elastic parameters, so the shear modulus and the second parameter in the Munir-Rivlin model, and we quantified the pointing effect. And we concluded that, okay, so the brain in torsion behaves as a Munir-Rivlin material. It has a positive pointing effect because, I didn't say that, but when, sorry, here the force is negative. So it means that when we twist a sample, we need to push to maintain it still. Okay, so it means that he's pushing up, so he's trying to expand. And this is the positive pointing effect. If the force was positive, it means that it would have meant that the brain was shrinking, like compressing, and we would need to pull it up to twist it. Okay, and then we also found out that the strain rate is as an effect on the data, right? So the behavior of the brain under torsion is strain rate dependent. So it depends on the speed at which we do the experiment. Okay, so what we are going to do next is to use the data we got from the experiments to so in UCD they have a model of the head. So we want to use our parameters and simulate a rotational impact and predict, well, give basically a map of the distribution of the strain in the brain. And we are working on that. And then, yeah, it would be good in the future to account for inhomogeneities, because we assume the brain to be just one tissue, but in reality it is made of white and gray matter, which have different mechanical properties. And because we concluded that the brain is a strain rate, so the behavior of the brain on torsion is strain rate dependent, it means that it's in a way viscoelastic, and so a better model would be a viscoelastic model. So we started doing experiments, so the tests on like stress relaxation tests, to test to test some viscoelastic properties, but we are not quite done yet. So that's it. This is the brain team. David, who taught me how to open pigs' heads, and that's Ashlyn in the middle that supervised the statistical analysis part, and also she found the machine, the Rheometer machine. And she was here actually in 2012. She was doing a PhD éco-tutelle with Corrado. Yes, with Corrado. Anyway, and that's Michelle, my supervisor. Okay.
Merci Valentina.
De
Est-ce que vous avez des questions? Valentina peut répondre en italien, en allemand, en français et en anglais, c'est ça, non? Grosso modo?
Non, ouais.
Et quand tu fais un test sur un échantillon, tu as toujours un comportement monotone de ta contrainte ou de ta force normale, t'as pas, je sais pas, des chutes,
oui, en fait, j'ai coupé les...
C'était la moyenne, j'imagine, sur les 5...
Oui, désolé, je l'ai pas dit, mais ouais, c'était la moyenne. En fait, il y avait aussi les dashed lines, ça c'était la standard deviation. Oui, en fait, ce qu'on voit ici, okay, can I speak in English? Yeah, so here you would see a decay after some time because the sample breaks. So the behavior is not elastic anymore, it's plastic, or is another range of. Yeah.
Le cerveau, c'est pas forcément un seul matériau, enfin continu. C'est, je sais pas, j'imagine plein de parties un peu.
Yeah, so what happens in the first part that I don't show here is because the machine needs some time to adjust the speed, so they're not reliable, the data I get before, because they're not at constant speed. Basically, it's accelerating until it reaches the desired speed. So I just cut them out. I didn't talk about, but there's we develop a filtering technique to just extract the relevant data. Thank you.
What kind of deformation rates do you have, like in actual impact when you have an accident? Is it comparable with this one, these values, or is it much higher?
Well, you have a combination of deformations.
Yeah, but in terms of shear rates, if you is it like of the order of 1 per second, or is it more?
Well, the thing is that that's very hard to say because what they measure is the acceleration.
Okay.
So we are trying to find a way to compare actually with what is available from the like car accidents or sport accidents. But yeah, so it's also hard because they have results for like frontal impacts.
Yeah.
So yeah, I have to do this. So I mean, I have to look into the literature and see what what.
I was also wondering, can you, well, in another way, can you do like oscillatory tests like people do in neurology, so that you can get G prime, G double prime,
yes.
relaxation time, and all the.
Yes, in fact, we are thinking of doing that as well. But yeah, we started with the stress relaxation test, so to test the strain dependence of the relaxation behavior, basically. But yeah, another like it's just different approaches, right? To get in the end a relaxation function, the parameters in the relaxation function. Yes. But the Rheometer can do the.
Usually, Rheometers can do it.
Yeah, oscillation. Yes.
Il y a encore une question?
Pour la description de l'effet pointine, vous avez des idées pour faire la modélisation? Parce qu'il y a toute une discussion pour savoir comment on fait la description à partir d'un matériau élastique ou si on se remet en configuration lagrangienne ou pas. Je ne sais pas si vous avez des idées dessus.
But so at the micro level, because I mean, with the Rivoli material, with the Rivoli model, so we also use the normal force data to fit the model. So that I think is enough an information we got.
D'accord, donc la reproduction actuelle, elle est satisfaisante?
I think so, yes.
Ouais, ok. Deuxième question sur la modélisation de la viscoélasticité. Justement, peut-être ça rejoint une question qui était posée tout à l'heure, à savoir si vous avez réalisé des cycles. On a une idée de la dissipation visqueuse pour savoir quelle est la nature de la viscoélasticité qu'on a.
So you mean if you're going to do
what kind of viscoelastic model do you want to develop for this effect?
That's an open question because I don't think there's a consensus on the viscoelastic modeling as well. It's still an open debate about how to model viscoelasticity. I personally worked on QLV, so quasi-linear viscoelastic models, because they are much easier to implement. Like if you want to fit stress relaxation curves, it's not going to be that hard to do it, like technically, I mean, numerically also. Whilst if you use internal variables model, for example, this requires much more numerical, like a much higher numerical power, and so I think I'd go for a compromise. So QLV, I think it gives enough information on viscoelasticity. In addition, with the brain, it's not easy to do the test itself. So what we can do, I'm not sure we can do oscillations actually, because it damages very quickly and it breaks very easily. Yes. So we would have to play with it.
Encore des questions? Bon. On va remercier encore Valentina. Merci.
Merci.